This conference will now be recorded.
Hello, everybody. Jordan Girth here from the National Weather Service Office of Observations. Thank you for joining us for the Satellite Book Club Seminar Series. This is session number 129. The title of today's presentation is Detecting and Tracking Smoke and Blowing Dust Using the ABI Aerosol Detection Product. Our presenter is Dr. Amy Huff, Senior Research Scientist from IM Systems Group. Our discussion after the presentation will be facilitated by Brian Mata, meteorologist from the National Weather Service Forecast Decision Training Division, FDTD. Just a few reminders before we get started that this session is being recorded. As you just heard, there will be an opportunity for Q&A after the presentation. We particularly encourage attendees from forecast offices and regional headquarters to post their questions in the chat, and we will field them in the order they are asked. We also encourage attendees to sign in with their full name, or if you have not done that and used an office account, please specify your full name when asking a question in the chat so we can follow up with you subsequently. I'd also like to remind everyone to check your spam folders if you are looking for TowerS communications. For NOAA.gov Google email users, unfortunately, some communication has ended up in the spam folder, and we don't want you to miss any of it. We are looking for future presenters for the Satellite Book Club. Please contact the TowerS team if you're interested. Perhaps you had a recent presentation at the AMS. We'd love to give you the opportunity to share that with your colleagues throughout the Weather Service. And the training team can help create training materials that may be unavailable or point you to materials that you may be unaware of. Brian Mata, the Office of the Chief Learning Officer, can help with that. I'd like to thank the TowerS team, particularly Kashad Bowman, the Office of the Chief Learning Officer, the GOZAR JPSS program, for all of their support, and thanks to all of you for being with us today. Without further ado, I'd like to introduce Dr. Amy Huff, who, as I mentioned, is a Senior Research Scientist at IM Systems Group, a contractor for the NOAA NESDIS Center for Satellite Applications and Research, or STAR. She has a PhD in chemistry from the University of California at San Diego and master's in meteorology from Penn State. Her research involves air quality applications of aerosol and trace gas observation from geostationary and polar orbiting satellites. Dr. Huff acts as a liaison to satellite data end users and promotes STAR atmospheric composition products through training and social media. She is also a Python enthusiast and has taught end users how to use Python for satellite applications. So we're glad to have Amy, the Satellite Book Club. Welcome.
Great, thanks so much, Jordan. So as you mentioned, I'm a member of the Aerosols and Atmospheric Composition Science team at NOAA's Center for Satellite Applications and Research, or STAR. So I'd like to acknowledge my colleagues. Pubu Siren, he actually developed the ABI aerosol detection product algorithm, and then Shobha Kandragunda, she is our science team lead. And so I'm actually going to turn off the camera because I have a lot of animations and I don't want to reduce bandwidth, but I'll turn it back on at the end when we have the Q&A. Okay. Okay, there we go. All right, hopefully everybody can see the slides okay. It looks like they're showing up in the little GoToMeeting. Of course, I'm going to talk about smoke and dust aerosols. They're a hazard to human health and welfare. They reduce visibility and they also degrade particulate matter air quality, including PM 2.5, fine particulate matter, and PM 10, coarse particulate matter. So smoke and dust impacts, they're becoming more frequent and more severe in recent years, due primarily to extended periods of drought in the US. So of course, smoke and dust, they can have impacts close to the sources of fires or arid regions where dust is lofted into the atmosphere. But also the aerosols can be transported sometimes hundreds or thousands of kilometers downwind. So the impacts can really range from the mesoscale all the way up to the synoptic scale. And so I probably don't need to stress the relevance for operational forecasters like meteorologists in the National Weather Service. I'm sure everybody's aware, but just to kind of highlight, obviously meteorologists, they're issuing warnings and advisories for hazards to ground and air transportation related to visibility. The National Weather Service provides support for air quality alerts and advisories that are issued by state, local, and tribal agencies. And then, of course, IMETs that are working at large wildfires, they need information, particularly about smoke, location, and transport in the atmosphere. And I just included a couple of examples. So this was a smoke on the top image from the McKinney fire last summer, and then a wall of dust from a haboob that moved through West Texas in March of 2021. All right, so the GOES are ABI aerosol detection product. It's a qualitative indicator of smoke and dust aerosols in a vertical column of the atmosphere. It's also called the smoke and dust mask. So aerosol detection product, it's available from the Advanced Baseline Imager on the GOES East and GOES West satellites. So ADP from the ABI sensor, it's what we call a binary, meaning it's a yes/no detection. So it's indicating the presence of smoke or dust aerosols in the atmosphere. And the reason why ADP is useful, particularly for operational forecasting, is because it quickly draws your eye to areas of smoke and blowing dust. So you can see the example here. This is from the GOES East or GOES 16 satellite. And so you can see in this particular example, this is from our group's Aerosol Watch website. The smoke plumes are shaded lavender. And then the dust plumes are shaded yellow. So sometimes, and I'll talk about this, sometimes in visible imagery, it can be hard to detect areas of smoke or dust. So the smoke is pretty thick in this case, so it's a little bit easier to see. But the dust is fairly faint. So the ADP clearly delineates with its yellow shading the areas of blowing dust. So ADP is available from all three of the ABI scan sectors in the flex mode or mode 6. And so that includes full disk and CONUS sector imagery every 10 minutes and imagery every 5 minutes from the 2 mesoscale sectors. And the spatial resolution is 2 kilometers. All right, so aerosol detection product, it's what's called a level 2 or derived product. So it's derived from the radiances from ABI bands. And so in the table here, you can see the list of bands. So ABI bands 1 through 7, and then 13 through 15 are used in the aerosol detection product algorithm. An algorithm is a formula that's used to calculate, or we say retrieve, the aerosol detection product. And so the ADP algorithm, it's based on threshold tests using these ABI bands. And the test separates smoke and dust aerosols from areas with clouds and clear sky. So that means that aerosol detection product, it's not retrieved or available over areas with clouds or snow and ice. And it's available only during the daytime because the ABI visible bands are used in the algorithm. So for those of you who are familiar with or have heard of at least the so-called Enterprise Processing System or EPS algorithm, so what that process is, it's a concept where one algorithm can be used for different satellite sensors. So for example, the ADP EPS algorithm will be used to generate aerosol detection product from both ABI and from VIIRS. And so actually right now, what's called the baseline ADP algorithm is in use, but there's a schedule to have the algorithm switch to the EPS algorithm on March 2nd. And so I just wanted, if people have heard about that, I just wanted to mention it. But actually for aerosol detection, there's no difference because the two algorithms, the baseline and the EPS algorithms, they're the same for aerosol detection. And I just included a few references down here that just discuss the algorithm in a little bit more detail. All right, so one nice thing about aerosol detection product is that the data files include a confidence flag. And so what this does is that it expresses the high, medium, or low confidence in the ADP retrieval, so the calculation of ADP using that algorithm. And so the confidence levels, this high, medium, or low, they're determined by 3 things. So one is how close a threshold test is to whatever the specified threshold is. So again, remember aerosol detection, the algorithm uses these threshold tests using the ABI bands. And so then also the solar zenith angle and the satellite view zenith angle. So I have an example here in the table. So this is one example for the critical test for dust detection over land. And so that test is the brightness temperature difference test. And so that's looking at the brightness temperature, the difference between the brightness temperature in ABI band 14 minus that in ABI band 15. And so you can see the different characteristics of the brightness temperature test causing the confidence level to either be high, medium, or low. And then I also wanted to point out, so the valid Solith-Zener angle range is less than or equal to 60 degrees, and the valid view zenith angle is less than or equal to 70 degrees. So if we're outside of those ranges, either the solar zenith angle or the view zenith angle, those observations are already automatically flagged as low confidence. And so you can see some examples here. So this is just an example on the top. This is the aerosol detection. And then on the bottom it's also the aerosol detection, but it's just showing the quality or the confidence flags. And this is for smoke from fires that were burning in northern Baja California in October 2019. So again, the top, the aerosol detection, the smoke flag, this pink shading is just indicating the location of the smoke pixels. And then here at the bottom, we can still see the location of the smoke pixels, but we have the added information of the confidence flag. So you can see most of the smoke is being detected as high confidence, and then there's a few pixels in this pink shading of medium confidence. So as a science team, what we recommend for users is for qualitative applications like forecasting to use all three confidences, so high, medium, and low. But then if you have a quantitative application like numerical modeling, for example, to just use what we call the top two confidences data, and that's just the high and medium confidence. All right, so I'm hoping that if anyone in this audience hasn't heard of ADP or they're not familiar with it, to give it a try. But there's a few things that you want to keep in mind. So one thing is that aerosol detection product is most accurate for thick smoke and dust plumes over dark surfaces. So for example, over water or over forest areas and vegetation. It's less accurate over arid and semi-arid bright surfaces. And that's because of the lower contrast between the aerosols and the surface. Another thing to be aware of is that gaps can occur in smoke detection for thick smoke plumes. On the first slide, you saw an example of a thick smoke plume, and some of the lavender shading was missing for the thickest part of the smoke plumes. And that's a known issue. That's actually, we do a lot of research to try to improve that. And the reasons are related to the algorithm. So the upstream cloud mask can misidentify thick smoke as a cloud. And then also in the algorithm, there's what's called a uniformity test. And that's just another way to identify clouds. And so often the smoke plumes, they're assumed to be more uniform than clouds, but if that's not the case, if there's a plume that has some thick smoke and some thin smoke, then this uniformity test fails. And so that part of the smoke plume can be flagged as a cloud. So that's something to be aware of. And then there's two kind of major known issues that occur most often at large satellite view angles and solar zenith angles. So the first one, I have an example at the top here. So this is a false smoke detection that can occur over thin clouds over land. So you can see with the lavender shading. And then another issue that can occur is there can occasionally be false low confidence dust detection, like in this example here of the yellow shading, and that will occur over bright surfaces. And these, as I mentioned, these most often you'll see these in the morning after sunrise, and then in the afternoon, the late afternoon before sunset. Oh, and this just reminds me, I just want to mention, so if this is an issue for you, these two kind of known issues with the false detections, if you use the top two confidences aerosol detection, that will automatically exclude the data that's outside the valid solar zenith angle and satellite view zenith angle. So then you won't have these issues. They won't occur and impact you. All right. So I say things like the ADP performs. It has a certain accuracy under certain situations. How do we know that? The reason why is because aerosol detection products, like all NOAA satellite products, it has to meet specific requirements. And so for aerosol detection, the requirement is for the probability of correct detection, or POCD. And so those requirements are listed here in this table. And POCD is calculated using a standard 2x2 contingency table, which is shown here on the upper left. So any of the forecasters that do, like, for example, tornado forecasting will be familiar with the 2x2 contingency table. And so POCD, it's determined from the number of correct detections from aerosol, the ABI ADP, aerosol detection, divided by the total number of detections determined by the truth data. And so what do we mean by truth data? So this validation process is done, it's quantitative validation with this so-called ground truth. And that's actually really difficult for ADP because there aren't really any ground truth data for smoke and dust mask. So we do an indirect approach, which is the best we can do. And so we validate the ABI ADP using smoke and dust classifications based on the Aerosol Robotic Network, or AeroNet matchups. And that's defined here in this lower table, those criteria. So AeroNet is a global network of ground-based sun photometers. And it's the ground truth for most satellite aerosol products, like aerosol optical depth, for example. And we also validate using the vertical feature mask matchups from the Calypso satellite. But I just, in the interest of time, I won't be showing those today. But I do want to show an example of what the matchups, the validation with the AeroNet data look like. So recently, GOES 18, which is now GOES West, the aerosol detection product underwent a provisional maturity review last fall. And so these are the results from the GOES 18, ADP, and AeroNet validation matchups. And so because NOAA was trying to move, was trying to move GOES 18 and have it become operational as GOES West as quickly as possible. The validation period for the ADP was relatively short. So it was from June 7th to October 31st last year. And so you can see in the tables, the smoke detection, which is the top table here, the POCD, it does meet the requirements of 80% over land and 70% over water. However, in the lower table for dust detection, the GOES 18 POCD was just under the requirements of 80% over land and water. So the POCD was 78.5%. And so that was due for a couple of reasons. First of all, this validation period, it was the wrong time of year for blowing dust. There were very few matchups for dust, and so that impacted the analysis. And also there were some issues with the GOES 18 ABI long wave IR bands. As you remember, the IR bands are used in the dust algorithm. So because of these issues, the ADP dust retrievals were degraded until after about July 15th. So that gave us an even shorter analysis period. So essentially, the chair of the review committee recognized that this near miss here, it wasn't an issue with the product itself. It was because of the analysis period. So GOES 18 did pass the provisional maturity review. And just for context, so GOES 16, that actually became provisional maturity back in December 2018. And you can see that it met, for smoke detection and dust detection, it met the requirements for the POCD. Okay. So why might National Weather Service forecasters want to give aerosol detection product a try? I know there's a lot of color composite or RGB imagery that's already out there that's really commonly used to identify smoke and dust. So things like GeoColor, dust RGB imagery, and then CIRA's DEBRA product. But the drawback with those is that the RGB imagery has to be manually interpreted. So a human forecaster has to look at it and using the different colors designate or differentiate between areas with smoke and dust. So the advantage with aerosol detection product is because it has a physical algorithm, it's automatically identifying smoke and dust. So visual interpretation, trying to distinguish those colors in the RGB imagery, that's not necessary with ADP. And so it's just aerosol detection product can just be another tool for decision support for operational forecasting. So it can really complement the use of the color imagery and just kind of provide additional information. So for example, this is a blowing dust event in the Chihuahuan Desert that occurred in December of last year, December 12th. So in this case, this is the dust RGB to start off with. This is GOES 16 or GOES East imagery. So you can, I think you can hopefully pretty clearly tell the magenta shading that's indicating the blowing dust in northern Mexico. There's a little bit over here too. Although sometimes this event is occurring in the afternoon, so it's pretty easy to see the magenta shading. If it's later in the evening or early in the morning, if the surface is cold, you can have this purple color that can make it difficult sometimes to distinguish between the pink magenta shading. So here now, this is the same event. Now we're looking at the GeoColor imagery. So again, in this area where there's the thick dust, it's relatively easy to see, I think, the dust. But again, a forecaster has to be kind of manually searching for this. If we add now, we overlay the aerosol detection product in yellow, it helps draw the eye to that area of blowing dust, and it makes it easier, or it's a decision support for the forecaster. And the other thing I wanted to mention is if you're using aerosol detection, you can actually do automated data analysis. So you could write some simple code that would actually, analyze, count, or pick out the number of smoke or dust pixels detected by ABI, and that's not something that is easy to do with the composite color imagery. So I just want to mention the access, the ways to get at the imagery. So from all three of the current GOES-R satellites, 16 and 17, 18, aerosol detection products provisional maturity. That means that the product's suitable for the broad user community and it's ready for operational use. So as I mentioned, GOES 18 ADP, it underwent its provisional maturity review last fall. It was declared provisional maturity on November 9th. And then of course, GOES 18 became operational as GOES West at 18 UTC on January 4th. So the imagery is available. I know it's available in AWIPS. It's also available from our Aerosol Watch website, and I just included a screenshot here. I understand sometimes that can be useful for like IMEX, for example, working out in the fields. And then also, of course, we have all the data files. They're available from NOAA's class, and also the new NOAA Open Data Distribution, or NOD, that used to be called the Big Data Program. And then we have documentation. So there's what's called the README documents that just give information about the ADP from GOES 16 and GOES 18. There's a quick guide, and then all of the involved details about the algorithm are included in the ATBD. All right, so I just want to show a couple examples of kind of in more detail of aerosol detection products. So this first one was a dust storm that occurred in Kansas in October of last year. So first we're looking at the GOES 18 observation, or excuse me, GOES 16 observations, GOES East. So this is the dust RGB on the left, just for comparison. So again, you can pick out, I hope, the magenta shading indicating the blowing dust. Super useful. And then on the right, we have the GeoColor, and then the ADP, again, just that bright yellow shading. I'm not sure what color it is in AWIPS, but whatever color it is, again, it's just a decision aid. It's just helping draw the forecaster's eye to kind of alert them that there is this area of blowing dust. And another thing we can do is, in this particular case, this location in Kansas, it was observed by both GOES 16, which is on the right, and then GOES 18 on the left. And so you can see this is now looking at, again, this is the same aerosol detection as we saw before, but this is just breaking it down by the confidence flags. And so you can see that both the coverage and the confidence levels are very similar for GOES 18 and 16. The difference is, in this particular case, is that the satellite view zenith angle is slightly larger for GOES 18, so you can see the pixels are a little bit bigger. And another thing is, you can see as the animation goes through, this area of yellow shading, this low confidence dust. That's the cutoff. You can kind of see the cutoff there. That's the cutoff of the GOES 18 satellite view zenith angle, so that low confidence dust is outside the valid satellite viewing angle, so that's why it's being flagged as low confidence. And that doesn't happen in GOES 16 just because of the different locations of the satellite. Okay, this is a smoke example. So this is actually now looking at GOES 17, which was the operational GOES West at this particular time. This is from September of last year. And there were a lot of wildfires in the Pacific Northwest. And you can see again the magenta, or excuse me, the purplish lavender shading that's indicating the smoke. It just helps draw your eye to those areas of the smoke plumes. And then again now, because of the unique position of GOES 18 and GOES 17 last fall, we have kind of two observations of the same area from the two different satellites. And again, you can see that the location and the confidence levels, the coverage are very similar. And again, I'd like to point out this area of the pink shading here from both satellites. Again, this is a cutoff of the valid satellite view zenith angle for GOES 18 and GOES 17. So outside that valid range, those smoke pixels are being flagged as low confidence. Okay, so I'm kind of running out of time. I just wanted to quickly highlight one of the things that we saw was improved performance of GOES 18 relative to GOES 17 during the so-called warm periods. And this is just a great improvement. So I just wanted to mention this quickly. So I'm sure, as you all know, you're familiar with the GOES 17 ABI loop heat pipe anomaly. And that caused the ABI focal plane module temperature on GOES 17 to rise higher than its intended temperature. And that in turn caused the GOES 17 ABI long wave infrared band radiances to be degraded during the warm periods. And this actually has a major impact, a major impact on aerosol detection because the dust algorithm uses the long wave IR band. So what we would see is a lot of low confidence dust detections, and then also some low confidence smoke detections as well. So this particular example, this is the full disk GOES 17 aerosol detections for August 28th, 2022. And that was a day when the focal plane module temperature in GOES 17 was really high. And so hopefully you can see there's a lot of this yellow shading and then this pink, light pink shading here, both in North and South America. So all of this pink and yellow shading, those are anomalous low confidence detections that are caused by the high GOES 17 focal plane module temperature. So now if we switch, so this is GOES 17, here's GOES 18. So do you see how all the yellow is gone? So this is GOES 17, again, GOES 18, and much of the pink is gone as well. So all of those anomalous GOES 17 detections, we don't see those with GOES 18. Which is fantastic. That's because the GOES 18 ABI, the focal plane module temperature, remains steady during the warm periods. So this is a big improvement for GOES 18 relative to GOES 17 for the aerosol detection. And I'm going to skip this slide. All this slide is showing is that I just showed one example on the previous slide. We actually saw this improvement with GOES 18 throughout the warm periods during the GOES 18 validation period that was basically the second half of last year. Let's skip through that. Okay, so this is my final slide. So again, if there's anybody in the audience, any of the forecasters that haven't used aerosol detection or maybe haven't even heard of it, I really encourage you to give it a try, see if it's useful for your forecasting routine. And just keep in mind the strengths, just like any satellite product or any forecasting tool, ADP has strengths and limitations. So the strengths are, the big one I think is that it automatically identifies the smoke and dust. So there's no need to rely on the visual interpretation by the forecaster. And that means that it complements the existing color imagery products that forecasters I think mostly routinely use to pick out areas of smoke and dust. And the confidence flags are another feature. That way you can kind of filter the aerosol detection product for your specific applications. Maybe you have a low tolerance for false alarms, and so then you would only want to use, for example, the high and medium confidence aerosol detection product. And of course, limitations, only during the daytime. We don't have retrievals over areas with clouds or snow and ice. It's a vertical column, so it's not really telling you anything about what's at the surface. You have to kind of look at a supplemental product to give you an idea if the smoke or dust is reaching the surface. And there's areas where there's the aerosol detection product is less accurate. And so finally, just a quick advertisement. Our group has a Twitter feed at Aerosol Watch. And if you're not already, you can follow us. We have product updates about our aerosol products, both from ABI and VIIRS. And then we also do event analysis. So thank you.
All right, thanks, Amy. We're going to have a Q&A period coming up. Let me just remind everyone to please use their full names in the chat when asking a question. And Lee will be posting a survey for some feedback in the chat room. Let's see. All right, let's start with some questions.
Okay.
In a week from today on Thursday, July 9th, John Evans and Lee Byerly will go over the next TowerS RPM version, that's number 23. And you can contact the TowerS team, Lee Byerly, Kashad, Bowman, for questions about the SBC or configuration of any of the satellite products like the ADP. All right, let's start with a question. Is ADP also available from VIIRS? And if so, how is that different?
Yeah, that's a great question. All right, I'm going to share my slides again here if I can. I actually have a backup slide just in case somebody asked that question. So there's a few differences. So the main difference is that VIIRS, because it has a wider range in terms of the wavelengths that's covered by its spectral bands, so VIIRS can use what we call a different algorithm path, meaning that it can give more information than what we get with the ADP from ABI. So VIIRS, not only can it tell you the location of the smoke and dust aerosols, it also gives information on the relative intensity, so thick versus thin smoke and dust. And so this is an example. This is a slide that's just talking about a Saharan dust transport event that occurred in June 2022. And so I just have a few images here of VIIRS aerosol detection. This is a composite from VIIRS observed from the SNPP and the NOAA 20 satellites. And so this, you can see from the scales at the bottom, so the smoke is in shades from lavender to purple, and the dust is in shades from light yellow to brown. And so again, the shading giving you an idea of the thick versus thin, the intensity of the dust. So we can see this is the Saharan dust ejecting off the coast of Africa. So you can see this dark brown shading that's indicating really thick dust versus the kind of lighter yellow shading indicating areas of thinner dust. So that's one of the main differences with VIIRS from the ADP from VIIRS versus ABI. The other difference is the spatial resolution. So VIIRS has higher spatial resolution. It has 750 meter resolution versus 2 kilometer resolution at nadir for ABI. And then obviously the other thing is that the ABI has nearly continuous observations, is much higher frequency of observations versus VIIRS, where we essentially get 1 or 2 observations per day for a given area because it's on the polar orbiting satellites.
All right, thanks, Amy. The next question is, and this might be for Lee, are the ADP confidence flags available in the AWIPS? Would Valerie or anybody else want to comment on that?
It does seem like they are. I just pulled it up.
Oh, good.
Yeah, I can verify that the confidence levels are available in the products that flow out to the Weather Service and that we're capturing them in our displays.
All right,
when you
thanks.
pick on the dust or the smoke, each of the 3 confidence levels display. And you can select them together or select them on and off in AWIPS.
All right, thanks, Lee. Next question from Mordechai Cohen. Is ADP only available from the ABI instrument, or can it be generated from MODIS? If yes, on the MODIS, is ABI or MODIS a better source for ADP?
Yeah, it certainly could be. MODIS has similar, and VIIRS have similar spectral bands, so it certainly could be. I don't believe anyone at NASA does provide an aerosol detection product for MODIS. I don't think so. And so what was the second part of the question, to use MODIS or ABI? Was that
which one would be better if both
Yeah,
are...
again, it really depends on the application. So the ABI is most useful if you need that very high temporal refresh. So if there's an event, a smoke or dust event that's happening on a very rapid time scale, or the hazards are happening quickly, then you would want to use the ABI. If it were something like I showed at the end, like a long range synoptic scale transport, so the Saharan dust, for example, VIIRS basically gave air quality forecasters in the Gulf states, so Texas, Louisiana, Florida got hardest hit by that event last June. It kind of gave them advance warning that Saharan dust was on the way. And so they could actually use the VIIRS ADP to help track the transport of the dust on the synoptic scale. So, which satellite center you use really depends on the application that you need.
All right, thanks, Amy. Lee Byerly says NAWIPS ADP is available for full disk, CONUS, and mesosectors.
Yes, that's correct.
He kind of talks people how to click through that in AWIPS if I
Okay, that's great. Yeah, and again, the frequency is a little bit different from the basic products like the level 1B products. So in mode 6, the full disk and CONUS aerosol detection is available every 10 minutes, and it's available every 5 minutes for the 2 mesoscale sectors.
All right, thanks, Amy. Let's see. Mordechai Cohen asks if ADP is only based for GOES CONUS coverage, or is there a movement or to use or validate it in other parts of the world, like Europe, Africa, and Asia? So I guess Mediosat and other geos, I guess.
Yeah, that's a good question. I don't know the Europeans, if I'm not 100% sure about that. I know that our group does some work with the AHI, the Himawari. I don't know if aerosol detection from AHI is a standard operational product, or if it's just a research product.
Okay, that's an open question. Maybe we could get back.
But I should mention the again, the strength of the enterprise processing algorithm, the EPS algorithm, is that it's one algorithm, so it can be applied to the sensor input from the Mediosats, from Himawari. So that is, and then that we're switching to that in March. So that is one of the strengths with that.
All right, that sounds good. Alex Flint asked a question. For verification work, he would suggest using bias, critical success index, or high-key skill score.
Well, we use the POCD. I can get back there. Here it is. Yeah, so we use the POCD, the probability of correct detection. That's the kind of requirement that NOAA has for the aerosol detection product, both for VIIRS and for GOES-R. But we also calculate other of the performance metrics as well. But I showed the POCD because this is the one that we have to demonstrate during the validation process that the GOES-R ABI aerosol detection product is meeting these requirements.
All right, thanks, Amy. Kashad says he will post the presentation slides today with the recording of this webinar. So if you want to dig deeper into the slides, feel free to download those.
Yeah, and again, I encourage, if anybody has any questions, don't hesitate to send me an email. I'm happy to, questions about how to use the product or interpret it or the validation, I'd be happy to answer any questions that people have.
All right, Bill Line has a comment. ADP is leveraged in conjunction with the dust RGB imagery and the newer AWIPS menu item on aerosol products. So
Oh, that's great.
it's getting its due in different places, I guess.
That's fantastic.
And Lee Byerly says the default for the dust pixels is a blue color in the AWIPS implementation.
Okay.
Scott Lindstrom has a question. Does preparation for GeoXO include work to extend aerosol detection to nighttime hours, especially for smoke?
Well, because of the, let me flip back here. Because the visible bands are used in the aerosol detection product, here they are. We can't actually calculate or retrieve the aerosol detection product specifically in the nighttime hours. But I do know there's a lot of research into this. For example, aerosol optical depth, which is a kind of a related product, which is essentially a detection for a quantitative detection for all aerosols, not just smoke and dust. There's a lot of research into using the day-night band, for example, on VIIRS to actually be able to calculate aerosol optical depth at night. So I guess the answer is no to specifically the aerosol detection product, but in the general sense of aerosol products, that's an area of ongoing research.
Yeah, I think that's a good way to couch it there, Amy. There probably is a way to do it. It just hasn't been.
Yeah.
Somebody hasn't really dug into deep enough to the different other products to be able to isolate and filter the way they would need to.
Right.
All right, one more from Mordechai Cohen. GeoXO is in the middle of program level requirements, and he suggests contacting Pam Sullivan to lobby for that requirement. Okay, I think that's the requirement for that Scott asked about, the detecting aerosols at night.
Yeah, it's not a requirement. It's not a construction requirement standpoint. It's just, this is the way the aerosol detection product algorithm works. It's just a fact of the scientific algorithm that we need the visible bands, and so at night you don't have visible radiances. So that's just one of the limitations of this particular satellite product. Like I said, all satellite products, all forecast guidance, model guidance, there's always strengths and then limitations, trade-offs. And so this is just one of the trade-offs with the aerosol detection products.
All right, we'll close with a comment from Mike Jabakowski. Another limitation of the MODIS sensor is, like VIIRS, it's on a polar orbiter covering the same point on Earth only 1 or 2 times a day.
Right.
So thanks for that, Mike.
Yeah, I mentioned the other thing is MODIS, we're really encouraging people, instead of using MODIS, to switch to VIIRS. MODIS is on Terra and Aqua, and they're really old. The advantage obviously is that they have a very long continuous observation period, but VIIRS has several advantages. One, it has a wider swath, so you don't have gaps in the observations over the equatorial areas. And then also VIIRS has a higher spatial resolution, so you're looking at 750 meters for aerosol detection product or aerosol optical depth, versus with MODIS, the aerosol optical depth, I think the highest spatial resolution is 3 kilometers. So anybody out there that's still using MODIS, we definitely encourage you to switch over to the analogous VIIRS product.
All right, thanks, Amy. And with that, we will wrap it up. And I guess I'll throw it back to Jordan.
All right, thank you, Brian, and thank you so much, Amy, for that great presentation. Really enjoyed it. A lot of great work going on with aerosol detection. The Satellite Book Club Seminar Series is going to continue a week from today on Thursday, February 9th at 12 noon Eastern Time. John Evans and Lee Byerly from our Tower S team are going to discuss the new Tower S RPM version 23. So If you're interested in what's coming to your AWIPs as far as satellite imagery and products goes, please join our TowerS team. And also, our TowerS team is always standing by if you need any help with configuring satellite products and AWIPs, or you have questions about the Satellite Book Club. We got email addresses right there on the slide, or you can also reach out in NWS chat. So with that, really appreciate your attendance for today. Hope you'll join us again next week. Hope your winter is going well, and take care. Thanks, everybody.